In this lecture, we will discuss CLIP, which was an anchoring inflection point for the success of vision language models. CLIP was introduced in the paper titled Learning Transferable Visual Models from Natural Language Supervision, published in the ICML 2021 conference by a host of different authors led by Alec Radford. The CLIP model provided a mechanism for text supervision in vision models. It paired an image with its caption using contrastive learning. Using a very simple approach, it outperformed fully supervised learning baselines on multiple datasets and also showed use as a zero-shot classifier, as we mentioned in the previous lecture. The official link of CLIP, hosted by OpenAI, which developed the model, has a lot of useful information which I would recommend you to look through. Recall that in our earlier lectures on CNN models for face processing tasks, we spoke about contrastive learning. We spoke about losses such as the triplet loss. Here is the example we spoke about even then. The triplet loss minimizes the distance between an anchor and a positive or similar sample and maximizes the distance between the anchor and a negative, which could be of a different identity or a different sample or a dissimilar sample. Here is a more tangible example. If you have an image of a dog in this case, and you have a corresponding text, a dog lying in grass, which matches with the image. We ideally want to learn image representations as well as text representations whose similarity is maximized. Whereas for the same text, if you had an image of an airplane, you want to learn image representations and corresponding text representations where we minimize the dot product or the similarity, or we are telling the model that this image and this text are dissimilar. This is the primary logic that CLIP uses, but makes it scalable to a very large data set. Here is the overall idea of how the CLIP model is trained. You provide both an image and text as an input. So in this case, you have an image of a dog and you also give the corresponding caption which says Pepper the Aussie pup. Both of these are sent through corresponding encoders, the image through an image encoder, the text through a text encoder, and the parameters of both these models are fine-tuned during the training process. Why do we say fine-tuned and not trained? Because you start with the image encoder being a ResNet or a vision transformer. Similarly, a text encoder being a text transformer. Once you get the embeddings of the images and the text, you can now organize all your images and text embeddings as a matrix, where our objective is that for a matching image and text, we want to maximize the dot product. Remember, dot product measures similarity between two entities. And for I2 and T1, which may not be matching, we want to minimize the dot product. That's the intuition that we want to follow. Let's see how this is actually implemented. If MI was a one-hot encoded label for a label vector for the ith image. So you could now imagine that mi is something like 1, 0, 0, so on and so forth, 0 all the way for the total number of image samples or text embeddings. Yim is the cosine similarity vector for the ith image sample. So this topmost row here could be YIM. One thing that we want to do here is, now you look at this term here called the cross entropy loss. Phi is the cross entropy loss. One thing that we want to do here with the loss is you want to match this cosine similarity vector with a one hot vector of the matching image and text, and ensure that you minimize the cross entropy between these two vectors. In other words, we want this first row, assuming I1 and T1 are the matching pairs, we want the first row to resemble a one hot vector with 1 in the first column. We similarly want to do the second row with 1 in the second column, the third row with 1 in the third column, and so on and so forth. This is one thing that we'd like to do. Now looking at the other notations here, similarly Ti is a one hot encoded label for the ith text sample. So just like how you have a one hot encoded vector for the image sample, similarly for the text sample you may have another one hot encoded vector which corresponds to the different images for that text. Now for T1, this could be the one hot corresponding vector across all images, and YIT is the cosine similarity vector for the ith text sample. So now we are talking about matching the column vector. So we take the first column vector and we would want this also to match a one hot vector where 1 is in the first place, and so on and so forth for the other column vectors in the matrix. So you have one loss that comes from matching rows or images, and you have another loss that comes from matching columns or the text corresponding cosine vectors. And the overall loss used to train our text encoder and image encoder is the combination or the average of these two loss functions. Now the pseudocode for clip, which is also given in their own paper, shows how simple it is to implement clip. You have an image encoder, you have a text encoder. IF and TF are the corresponding embedding outputs of the image and the text respectively. Now you compute, you take the IF and multiply it by a weight matrix, similarly TF multiplied by a weight matrix, and whatever corresponding embeddings you have, you normalize them. Then you compute your logits as the pairwise cosine similarities between all your image embeddings and text embeddings, and there is a exponential scaling factor that you use to just scale up your logits. And finally, you simply implement your cross entropy loss on the row vectors and column vectors that we just mentioned. Very simple to implement. Now, how can this be used in a zero-shot manner, what we have been claiming so far? Clearly, it can be used in a supervised manner where you have for every image a corresponding label, and you now match your image and text and give a corresponding output. How can this be extended to zero-shot learning? Let's quickly recall what zero-shot learning means. Unlike supervised learning, the model is trained only on scene class labeled data in zero-shot learning, but the model is evaluated on unseen and seen classes. This is also called generalized zero-shot learning. We know that traditional image classification models, where you use pure supervised learning, are limited to a fixed output label space and may lack generalizations to new labels at inference time. When we talked about zero-shot learning in one of the earlier weeks, we talked about methods like relation networks or generative approaches like FCLS WGAN or meta-learning methods to address zero-shot learning. This visual shows an illustration of zero-shot learning where you have a manifold of known classes for which you are given the images corresponding to the labels, and then you have unknown classes where you only know the labels but no images corresponding to those labels, but when they are given at test time or inference, the model has to be able to classify those images into those unseen classes. So coming back to CLIP, how does CLIP handle zero-shot? Once you have trained your image encoder and text encoder, you can now create a dataset classifier from a labeled text and simply do zero-shot prediction on the text. For example, if you have a new text corresponding to a new class, let's assume dog was a class that we had not seen during training. Now you have a new label called dog. You create a caption out of the dog that simply says a photo of a dog. Now you pass it through the trained text encoder. You take the image, pass it through the trained image encoder, and simply use your cosine distance between I1, the image, and all the text that you have so far. Take all the dot products, and wherever you have the highest dot product is where you have the highest similarity, and you simply give out that text label as the answer for the given image. This label, dog in this particular case, may not have been seen during training at all. How does this magically happen? The hope here is that the image encoders and text encoders have learnt such good image and text embeddings that even for unseen classes and images, it is able to map these two embeddings to a space where if we compare the image and text embeddings, the correct matching automatically happens even for unseen classes. Obviously, this has to mean that the model was originally trained on large amounts of data. That's when it can scale to new labels. And this is something we'll talk about in the next few slides as to what data sets they used to train CLIP. Existing crowd labeled data sets like MS-COCO, Visual Genome, YFCC 100M are possibilities for training CLIP. However, data sets like MS-COCO and Visual Genome are relatively small. They have about 100,000 images each. And YFCC 100M is a good data set, but it has about 15 million natural description titles with corresponding image matches, which is about the same magnitude as ImageNet. You could be wondering how that is the case, because ImageNet is supposed to be about 1 million images, 1.2 million images. But please keep in mind is that images, the ImageNet dataset originally had about 14 to 15 million image and corresponding text, of which only 1 million was used in the original benchmarks. But the dataset by itself has about the same number of image text matches as YFCC 100M plus or minus a few. Given these to be relatively smaller datasets, the authors of CLIP created their own dataset called the Web Image Text or the WIT dataset, which consisted of 400 million image text pairs curated from various publicly available sources on the internet. This was their magic potion, if you can say so. Once you learn text encoders and image encoders, that match these 400 million pairs, their claim is that now you could use the same encoders to even classify on newer labels as zero-shot classification, as we mentioned. This web image text dataset is somewhat similar to the web text dataset that was used to train GPT-2. We also spoke about the web text 2 dataset in the previous lecture. So web image text was in some sense the extension of those kind of datasets for the vision language confluence. What were the other considerations, design considerations that they had while training their model? For the vision encoder, they tried two lines of models, the ResNet line of models and the VIT or the Vision Transformer line of models. In the ResNet variants, they used ResNet 50, ResNet 101 and EfficientNet style model, where they scaled up to 4x, 16x and 64x of ResNet 50. With VITs, they used the base model VIT-B16, they used VIT-B32 and they also used VIT-1114, which is the largest model. Okay. Recall that when your patch size becomes smaller, the model becomes bigger in VITs. And for the text encoder, they used an adaptation of the standard transformer similar to the vanilla GPT. In terms of optimization, they used the Adam optimizer, a temperature scaling factor of 0.007, we also saw that in the pseudocode, a batch size of 32,768, and they trained the model for 32 epochs. An obvious query in your mind could be, how long did the model take to train and what kind of hardware? So for the largest ResNet model, it took them about 18 days to train on 592 V100 GPUs, and for the largest VIT model, it took them about 12 days to train on 256 V100 GPUs. Now let's see some of the impressive results that they reported based on this very simple approach. Here are some results of their zero-shot transfer. So what they showed here is that CLIP outperformed baselines on a wide variety of datasets. Across a 27 dataset evaluation suite, a zero-shot CLIP classifier, keep in mind that the final classification on those set of labels are on images where you had not seen those labels before. It outperforms a fully supervised linear classifier fitted on ResNet 50 features. What do we mean? You train a ResNet 50 model or take a pre-trained ResNet 50 model, you get the features out of the ResNet 50 model. Now train a linear classifier on those features on all the labels, which means we are comparing zero-shot CLIP to a fully supervised linear classifier on ResNet 50 features. On 16 of the 27 datasets, CLIP outperforms all the baselines. It seems to underperform on a few datasets which are generally specialized on specific domains, like it performs the worst on the Eurosat dataset, which is a satellite image dataset. So one takeaway you can observe here is that CLIP is good for generic tasks, but as you go towards more specific domains or hyper-specific tasks, CLIP requires fine-tuning on that dataset. Here is another example of the performance of CLIP on zero-shot transfer. They studied the number of labeled examples per class that are required to train a linear classifier on the CLIP feature space that gets you the same performance as the zero-shot CLIP classifier. Right? Let's try to understand this better. We already spoke about how CLIP does zero-shot classification. Now imagine that we took the CLIP feature vectors, okay, the image feature vectors that we get. Now you train a linear classifier on those CLIP features how many images did you need on each of those zero shot classes to match your original zero shot accuracy itself. Okay, that's what was measured in this experiment. And you see that for a majority of data sets, the model needed quite a few examples of clip features itself to match the clip zero shot performance. Okay. You could argue that its simple cosine distance matching was actually better than even training a linear classifier on the clip image features. Only in 2 data sets it could not do as well. Once again, the Eurosat dataset being one of them, which is a specialized domain dataset on satellite images. Here is another of their experiments where they studied the linear probing performance of clip, which is, in other words, a linear classifier trained on the clip image feature representations. You see here the solid stars and the hollow stars that correspond to clip models. You see that they are on top in both the experiments in 2 different cases, one in Kornblith et al.'s 12 datasets and the other on the 27 datasets that we saw on the previous slide. In both these cases, clip outperforms pretty much all the baselines, which are standard baselines like efficient net and so on and so forth, including even VITs. And what is interesting to observe is that as you allow the model more capacity, which means as you allow more G-flops per image, clip only does even better than your baseline models. Here is their experiments on the few shot learning performance of clip as compared to its zero shot performance. You see here that the zero shot performance of clip is right here, where it takes 0 samples from each of the zero shot classes. And even if you give a few samples for competing models, you see that all of these models don't perform as well as clip unless you go and give at least 16 samples for each of those unseen classes. And a linear classifier built on the clip features significantly outperforms any other baseline in this context when it receives 16 samples for those unseen classes. One last result that we'll reproduce from their work is the robustness of clip to distribution shifts. Here is an interesting result where they consider the banana class, which is a class that is shared along many of the natural distribution shift datasets. You see that you have the ImageNet dataset, ImageNet V2 dataset, ImageNet R dataset, ObjectNet, ImageNet Sketch and ImageNet A. Okay, there are about 5 of these datasets other than ImageNet that contain the banana class. And what we are doing here is we are comparing zero shot clip performance to a ResNet 101 model that's trained on base ImageNet on this first row here. Right? We want to see how well it classifies the same banana class on newer other kinds of data sets that may have a distribution shift. In the first row, you see that zero shot clip performs as well as a ResNet 101 trained on ImageNet itself on a banana class. Okay, that's the base performance. Now, as we go to the other data sets that have a distribution shift, you see that the ResNet 101 model that was trained on ImageNet, its performance keeps dropping as the distribution shift keeps increasing. ImageNet A is one of the most challenging distribution shifts, followed by ImageNet Sketch, ObjectNet, ImageNet R and ImageNet V2. And you see that the ResNet 101 model that was trained on ImageNet, its accuracy keeps dropping as we go to higher and higher distribution shifts. But now you see that the zero shot clip model pretty much maintains its performance across all of these cases. In fact, in some cases having significant improvements over the base ResNet 101 model. These results are fairly impressive for an approach that's, as you can see, simple to implement, but of course they trained it on a very large data set to be able to obtain these results. For more details on the CLIP model, please see their original formal website for describing the CLIP model, and if you'd like to know more about the code, please also look at the Hugging Face link for CLIP.